We're going to look at section 2.2, interpretations of the derivative. The derivative at a point we saw is the following definition. So we let f be a continuous function on an open interval and let c be in that interval. The derivative of f at c, denoted as f prime of c, is f prime of c is equal to limit as h goes to 0, f of c plus h minus f of c all divided by h. As long as that limit exists, then the derivative at that point exists and the function is differentiable. We saw that this derivative came from the limit of a difference quotient. And that meant that the derivative is telling me an instantaneous rate of change. How fast is the function changing at a certain value? So we're going to look at interpretations of the derivative using those rates of change. So we use the understanding that a derivative is an instantaneous rate of change, and we're going to look at how that can be applied in different scenarios. I want to start out by looking at the units for the rate of change. Our derivative notation was dy over dx, derivative of y with respect to x. And notice that in terms of slope, the units that we're changing in the numerator of the fraction are units in the y value. And the units that we're changing in the denominator of the fraction are units in the x value. When we talk about a rate of change, we are talking about the change in y per change in x. So the units of change in y per units of change in x. Let's think about how that could be used in an application setting. Let's look at example 1. One of the fundamental applications of derivative is by letting our original function be a position function. And we're going to let this original function be a position function where our variable is time. Our variable that we're going to use here now is the letter t. T will stand for time. If you think about a rate of change, that means the derivative is the change in position per unit of time. Think about what that actually means. If we're changing our position per unit of time, or rather if our derivative is measuring a change in position per unit of time, well, that means my derivative is a velocity or speed. Think about how this would work if your position were measured in miles and your time were measured in hours. Your derivative would be change in miles per change in hours. So it'd be miles per hour. And so if we have a position function, s of t, and we let t be some unit of time, then the derivative is the velocity function or a speed function. We tend to use velocity in mathematics, and here we've denoted it s prime of t equals v of t. So the derivative of the position function is equal to a velocity function. Let's look at another example. In fact, this is another fundamental example. What if our function were the velocity function, where t is time? So we take the velocity function v of t, where t is time, and we want to take the derivative of a velocity. Now that means the derivative is a change in velocity over unit time. If you think about what a change in velocity per unit of time is, it's basically telling you how fast your speed is changing. So how fast your speed is changing. Think about what that means in practical terms. Well, hopefully you thought about it for at least a second. The derivative there has to be acceleration. So the function v prime of t is equal to a of t, or the acceleration function. Remember, we're talking about velocity. So the change in velocity is acceleration. As you get faster, you are accelerating. As you get slower, you are decelerating. By the way, the acceleration function is positive when we're accelerating, and when you're decelerating, the acceleration function is negative. So when you're slowing down, the acceleration function is negative. If you're speeding up, the acceleration function is positive. Let's look at another application. This one comes up a lot when you're dealing with business or manufacturing. We let our function be the manufacturing cost, where X is going to be the number of units produced. Our derivative, therefore, is the change in cost per unit produced. So what is the total change in cost per unit produced? Well, if manufacturing cost is our function, the derivative is something called the marginal cost. And roughly, that's the cost of producing one additional unit. So C prime of X is called the marginal cost function. The derivative of the cost is a marginal cost. If you're looking at in other business settings, you could have talked about the profit rather than the cost, or the revenue rather than the cost, and they'd all be marginal profit, marginal revenue for your derivatives.